So we will cover mathematics in artificial intelligence. So in arithmetic, we have basic arithmetic operations that is fundamental for all computations in AI algorithms. That is that we know that addition, subtraction, multiplication, division used in calculations within neural networks, cost functions, and gradient or descent optimization, and many more things. Then number system, natural numbers, we represent counts like the number of layers in a neural network or the iterations in a training loop. Now integers used for indexing data sets, labeling classes, and discrete parameter settings. Rational numbers, they represent probabilities and ratios such as learning rates and weight adjustments. Real numbers representing continuous data, model weights, activation input outputs, and loss values, and many more things. Complex numbers applied in signal processing and in certain neural networks dealing with waveforms and transformations. Hypercomplex numbers used in 3D rotations and orientation calculations in robotics and computer vision. Then octonions explored in advanced AI models for high dimensional data representation and theoretical research. Modular arithmetic, basis for hash functions, cryptographic algorithms, and pseudo number random number generation using security and data shuffling. Divisibility, important in cryptographic algorithms for secure communication in AI systems. Prime numbers, fundamental in cryptographic protocols, ensuring data security in AI applications. Factors and multiples, used in AI, used in algorithm optimization and understanding computational complexity. Fraction decimals, they represent probabilities, learning rates, and thresholds in models. Percentage express model accuracy, error rates, and performance metrics. Exponents and radicals, they describe growth rates in algorithms, exponential decay in learning rates, and activation functions like exponential linear units. Logarithms used in loss functions, measuring entropy in information theory. Time series data modeling, iterative algorithm steps, and convergence analysis. Then in algebra, elementary algebra, variables and expressions represent features, weights, biases, and outputs in models. Equations and inequalities formulate constraints and objectives in optimization problems. Polynomials used in regression models and to approximate functions in neural networks. Factoring to simplify expressions in symbolic AI and computational efficiency. Rational expressions still model relationships in data and complex functions. within the AI algorithms. Modern relationships between in data and complex functions within AI algorithms. Linear algebra, vectors and vector spaces. They represent data points, features, and weights in models. Essential in word embeddings. So represent data points, features, and weights in models. Essential in word embeddings and image data also. Matrices and determinants, they handle data sets, transformations, and operations in neural networks. Crucial for batch processing. Systems of linear equations solve for parameters in models like linear regression and least squares. Eigenvalues and eigenvectors key in dimensionality reduction techniques like PCA and in understanding covariance matrices. Inner product spaces may measure similarity and compute projections in high dimensional spaces. Linear transformation describe operations in neural networks such as layer transformations and feature mapping. Abstract algebra groups, symmetric groups assist in pattern recognition and in invariance in computer vision. Rings and fields underpin cryptographic algorithms for secure AI communications. Provide advanced frameworks, modules, and algebras for understanding complex structures in AI models. Boolean algebras. Then Boolean algebras, fundamental in logic programming, decision trees, and binary classification tasks. Category theory offers high level abstractions beneficial in understanding deep learning architectures and functional programming aspects in AI. Geometry, Euclidean geometry, basics for computer graphics, image processing, and spatial reasoning in robotics. Non Euclidean geometry, hyperbolic geometry, embedding hierarchical data and representing complex networks efficiently. Analytic geometry used in computer vision for object detection and in representing data geometrically. Differential geometry used in AI, manifold learning, and understanding the shape of data distributions for dimensionality reduction. Topology, general topology, concepts like continuity and compactness are important in ensuring the convergence of learning algorithms. Algebraic topology, topological data analysis, extracts features based on data shape, useful in complex pattern recognition. Trigonometry, trigonometric functions, signal processing, analyzing periodic data, and in the design of certain activation functions. Polar coordinates helpful in feature extraction for circular patterns in image recognition. Feature extraction for circular patterns in image recognition. So, calculus, differential calculus, fundamental in training models using gradient based optimization method. Integral calculus computes areas under curves for probability distributions and loss functions. Multivariable calculus, essential for understanding and optimizing functions with multiple inputs in machine learning models. Differential equations model dynamic systems and time series data as seen in recurrent neural networks. So that is all for this. We'll continue in the next session.